lesson 6.1, we're going to start talking about the normal distribution. So the normal distribution is a continuous probability distribution for some sort of random variable. And it has a certain shape, okay? It is going to look like this. Notice it's symmetric and bell-shaped. And we'll get into that in the properties. But what we mean by it's completely defined by its mean and standard deviation. I know these are pretty small, you may not be able to see them, but here in the middle of this, that's the mean of whatever, of our distribution. So that's mu. This value is the mean plus one standard deviation, so one standard deviation above the mean, one standard deviation below the mean. Then this is mu plus 2 sigma, 2 standard deviations above the mean, 2 standard deviations below. You can go 3 above and 3 below. This should look really familiar when we talked about the empirical rule. Remember how we said that 68% of values were within 1 standard deviation above and below, and 95% of the values were within 2 standard deviations above and below. So this should look pretty familiar to you. So properties of a normal distribution. So when we say something is normally distributed, there are a few things that we mean by that. The first thing is that it's symmetric and bell-shaped. Both of those things have to be true. So you can see over here, this first one is bell-shaped and it's symmetric. And right here, this is the mean, median, and mode. And they're all the same, or really, really close to the same. Notice this one over here, this is definitely a symmetric distribution, but it's not bell-shaped. This is a bimodal one, so this is not normal, okay? That is not a normal distribution. So a lot of the stuff that we're talking about with this unit, we can't apply to this one. The next property of a normal distribution is that it is completely defined by its mean and standard deviation. And that's what we just talked about, like with the empirical rule. Our mean is always here in the center, that's mu. 1 standard deviation above the mean and 1 standard deviation below the mean. So you've got mu plus sigma and mu minus sigma. We call these things, I don't know why, that was terrible. We call these points inflection points, here and here. And that's the 1 standard deviation above and below the mean. Those of you who are in calculus, inflection points have a meaning graphically as well. We'll get into that later on. Our third property is that the total area under the curve equals 1. So we can find the probability that we land at a certain location in this, okay, by taking the probability that whatever variable we're looking for is less than a particular value. So that's the area under the curve to the left. Okay, so that's going to be really big for us, but we can find the area, by finding the area under the curve, that gives us the probability that we land at that certain spot. And finally, x is a horizontal asymptote. Now, I know it looks like the distribution ends here at 3 standard deviations above and below, but it actually keeps going in both directions. It gets closer and closer to the x-axis, so it's possible to have something 5 standard deviations below the mean or 10 standard deviations above the mean. It would just be really, really unlikely because those get so close, but it's still possible. Now, there are an infinite number of normal distributions. All of these are pictures of different normal distributions. Like I said, they're completely dependent on the mean and standard deviation. So in this graph, mine's in color, I know yours isn't. The blue, red, and yellow ones, they all have the same mean, okay? But their standard deviations are different. Blue has a pretty small standard deviation, whereas yellow's is really big. Green has a completely different mean, it's way over here. These are all normal distributions. They just have different means and different standard deviations. So depending on whatever you're measuring, your normal distribution might look different, but they're still have all the same properties. The area underneath them is 1, and we can calculate probabilities. So a really important idea with our calculations, in order to simplify them, we convert normal distributions to the standard normal distribution. So rather than having like the mean ACT score is 22 with a standard deviation of 2.6 or whatever that is, we can convert it to the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. And this is what it looks like. Okay? The properties of it are listed on page 321. They're the same properties from the front side of this page. So when we convert to this standard normal distribution, we convert to z-scores. We dealt with z-scores back in chapter 3, I want to say. So we can convert to z-scores. This formula should look really familiar. A z-score is found by taking whatever x value you have minus mu, the mean, divided by sigma. That's your standard deviation. And the z-score tells you how many standard deviations above or below the mean you are. In the next video, I'll show you how to actually calculate these.